Good morning, dear learners. In last lecture number 4, we have seen about the various types of lattice, unit cells. Basically, 4 unit cells are there. Depending upon the combination of these basic cells, basic unit cells, we have seen various types of crystal lattice. So, such as triclinic, depending upon the length of the edges and depending upon the of angles such as alpha, beta and gamma. I mean, depending upon their values and depending upon the vector A, B and C, the edges of the unit cells, either they are mutually perpendicular to each other or two of them are equal in length and three of the angles are having same measure, or depending upon such type of nature of the edges and angles, we have seen different lattices, that is triclinic, monoclinic, orthorhombic, tetragonal, cubic, trigonal, hexagonal. I mean, if we all add, there are 14 unit cells. So this concept we have seen in last lecture. Now we come to this point, that is basis. Question arises, what is basis? Very simple it is. The basis is nothing but the arrangement of atoms associated with each lattice point. Each lattice point, we have seen in previous lectures, the lattice points are red, green. I have shown in that figure, you remember, imagine. The basis is the arrangement of atoms associated with each lattice point. Sometimes there is only one atom associated with the lattice point. I mean, there is one atom associated per lattice point, that is a monoatomic lattice. But in general, usually there are more atoms associated per lattice point. Such arrangement is nothing but basis. Remember. So basis is nothing but, now clear, that is the arrangement of atoms associated with each lattice point. If there is one and only one atom associated with the lattice point, we say it is a monoatomic lattice. But in general, usually what happens, there are more atoms associated with per lattice points. Clear? Now let us turn towards the operations. I mean, symmetry operations. Symmetry operation is an operation that can be performed either physically or imaginatively on crystal with reference to plane, axis and a point within its mass. For example, I'll tell you, suppose you have a square. Imagine, you know, square. Imagine square, how it is. Suppose this is a square. Then you take a point at the center here. Suppose this point is A. Through this point, if a line is allowed to pass perpendicular to this surface, then if we rotate either clockwise or anti-clockwise through 90 degrees, this figure, then what happens? It becomes as it is. I mean, this is what, by using the axis or by using a point. Sometimes what happens, if we use a diagonal, if we utilize here plane along this diagonal, then what happens? If we rotate again, what happens? All these things uh, gives the operations, symmetry operations. Symmetry operations can be performed by using or with the help of references, plane, axis and point within the mass of the structure. Crystal structure, mass of the solid, like. Now, question arises, what are the types of symmetry operations? There are 4 symmetry operations. They are shown here. Translation operation, reflection operation, rotation operation and inversion. Among these, first operation, if we think about translation. So in this case, what happens whenever such an operation is utilized on a lattice, then what happens? See, this operation, translation operation, holds on lattice only. Strictly you remember. And remaining 3 operations, what are those? Reflection, rotation and inversion. These can be applied, or they are applicable on any object, any solid, any crystal. But in case of translation operation, what happens? This holds on lattice only. Clear cut, this point you remember. Now, what is translation operation? Whenever an operation is applied on a lattice point, and if its position is R, a lattice point having position R, and operation is applied on such a point, and its position is suppose changed to R dash, from R to R dash. Position of the lattice point is going to change because of what? Because of such operation. Because of operation, its position changes from R to R dash. But remember, in such a way that surroundings of R and R dash remain same. There is no change in the surrounding of R and R dash. In short, we can say surroundings of R and R dash are identical. The operation due to which the position of the lattice point is going to change from R to R dash without changing its surrounding, or we say that the surrounding is as it is. Their surroundings are identical in nature, then such an operation is said to be translation operation. Clear? In short, I will tell you, whenever operation is applied on a lattice point, the position of the lattice point changes, no doubt, but their surroundings, surrounding of the original position and the final position of the lattice point remains unchanged, identical. Such operation is called as what? Translation operation. Remember. Now let us turn towards the remaining 3 operations. These operations already I have told you. These operations hold on any object, and we say collectively called as point symmetry operations. Reflection, rotation and inversion, these operations are called as, we say together collectively called as point symmetry operations. Symmetry operations. Symmetry operation is an operation that can be performed either physically or imaginatively on crystal with reference to plane, axis and point within its mass. Already we have seen. I mean, the symmetry operation we can perform either physically or imaginatively for the study of the crystal. But with the help of what? Again, plane, axis and point within its mass. Some symmetry operations achieved by using or selecting the planes which shows mirror images. Rotating the crystal in particular axis. For example, simple example I will tell you. You take a cardboard, rectangular cardboard, and you take a plane from the midpoints of upper surface, upper edge and lower edge, and you apply a cut like this. Then what happens? If we hold together those half planes, those half parts of the rectangular cardboard, then they will collide with each other, they coincide with each other. So in this way, so there are various operations. Here, select the plane which shows mirror images, rotating the crystal in a particular axis. Operations we can achieve by different ways. Select the point which shows equidistant also. Plane of symmetry. It is an imaginary plane which passes through the center of a crystal, can divide it into two equal portions which are exactly the mirror images of each other. I mean, a plane utilized as operation, it gives us two equal positions or portions, and they are what? Exactly the mirror images of each other. There are such operations also. Axis of symmetry or axis of rotation is an imaginary line passing through the crystal such that when the crystal is rotated about this line, it presents the same appearance more than once in one complete revolution. That is in a rotation through 360 degrees. For example, you take a cuboid and allow to pass a line through its center, front surface and back surface. And if either you clockwise or anti-clockwise, you rotate it how much? Through 360 degree. Yes, if such a cuboid is rotated through 360 degree Celsius, 360 degree, then what happens? It appears same as the previous. Four axis symmetry on the rotation about the axis of, if the faces of same view occur two times, the axis is termed as dyad axis, that is 360 upon 180 two rotations. On the rotation about the axis, if the same faces or same view occurs three times, the axis is termed as triad axis, that is three rotations. So in this way, there are various number of rotations depending upon nature of the crystal and depending upon the nature of the crystal and positions. Thank you. Remaining matter we discuss in next lecture.